Hello and welcome back to my series of pre-development videos exploring a wide variety of topics to prepare for my senior computer science capstone coming up in the fall. Today we'll be exploring Unity's compute shaders to generate fractals, these geometric objects with self-similar features. This is one of the most famous of them all, the Mandelbrot set, and the one that we'll be exploring today. In Unity, we'll start by creating a canvas with an empty raw image element. Then we'll create a manager class that creates and configures a render texture on the fly. This class will also handle the communications to and from CPU and GPU land. We start by getting an identifier of the shader's entry point function. Our render texture, along with other variables, will be passed to our compute shader through these set functions. Finally, we'll dispatch the request to the GPU with how many groups of workers we want to use at the same time. On the shader side, the first thing we've got to do is redefine the variables we sent over. Next, we have this num_threads attribute. These values need to be multiples of the values from our dispatch function from earlier. The last key variable we need to discuss is this ID variable. Since our function gets mass called onto the GPU, this tells us what part of the problem each worker is being assigned. In the context of render textures, this ID variable is our UV coordinate of our render texture. Now we can start talking about fractals. Aside from looking cool, one of my favorite parts about fractals is that the math you need to build them is pretty light. These types of fractals rely on complex numbers, where we define I as a square root of -1. The most we're going to need to know about these is how addition and multiplication work. Addition is nice, as we just add the real and imaginary parts for both complex numbers. Multiplication, that one gets a little twisted. If you have ever FOILed polynomials, this is the same process. But before you simplify everything, anything that has an I squared turns into a -1. If we translate this to code, we end up with this. And now we're ready to talk about the function that actually creates the Mandelbrot set. This complex C variable here is actually our pixel coordinate on our screen, so you can treat that as our UV coordinate. We'll treat the horizontal axis of the real valued part and the vertical axis as the imaginary part to make it a complex number. Now this function is actually recursive, so the output of the function gets to be the input for the next iteration. You can imagine that if you started your function with the number 2, you can expect the output to balloon towards infinity. But for some complex values, you end up bouncing around chaotically before eventually escaping to infinity. But for others, you just never escape. You bounce around forever. The idea behind coloring these fractals is how many iterations of the function did it take for you to escape. To implement this, we can run our function over and over until we pass an escape check, or if we hit an iteration limit. If we divide the number of times it took by the iteration limit, we can map this 0 to 1 value to blend between different colors. We'll also add in support for zooming and panning while we're at it. Now, we can make this a lot more interesting by switching from setting RGB values to setting HSL values, specifically hue. In this color space, as we increase hue, we end up looping through all of our colors again. So if we multiply our hue by, say, 3, we get 3 loops of the color ring. Now, we need to convert HSL back to RGB, and this is a nice spot to start hand-waving some of the details. Another math tweak that we can do is to eliminate this banding between each color. This double logarithm here gives us an approximation of just how many fractional iterations were needed for us to escape. One final thing we can do is add in functionality to increase and decrease the amount of iterations. And with that, we've got a quick and cool visualization of the Mandelbrot set using compute shaders. If you're interested in more of these videos, consider subscribing. In the next video, we'll be going back to the prototyping project, but with compute shaders as a new tool. Hey, editing Bat here. So, I forgot to mention something, just a little bit important. With the approach that we're using here, we're going to be restricted by floating point arithmetic. When we zoom in enough, the floating point math is going to break down. With my laptop, the GPU can only use 32-bit floats, so I noticed the change pretty quickly. There are some technical ways around this issue, but you'll be trading off precision for performance. Since my laptop is already on the verge of melting, I'll see you guys next week.